Okay. What are we making when we make a Grignard reagent? A nucleophile. So our goal of making the Grignard is to get a nucleophile, an active carbon nucleophile, which are incredibly reactive. And we want to take that and react it with something else so that I can get a larger structure. What is the issue with the bottom?
There's 2 reactive sites in each one.
I'd elaborate. It's not just 2 reactive sites.
There's both a nucleophile and an electrophile.
It has both the nucleophile position, which is good, that's what the Grignard's supposed to have, and an electrophilic site. That means when I take the Grignard reagents, I take those and try and make those. What happens? I form the Grignard, and now the Grignard reagent can react with itself. That can be intramolecularly, as some people were trying to draw. What's the issue with the intramolecular? And I think all of these. The angle strain of trying to bend in to do that reaction. Okay? So I'm not going to freak out at that because you came to the right idea, but the angle strain is probably not going to work. What are they more than likely going to react with? Other molecules or other Grignard reagents, just not the way we want them to. Okay? So again, when we're looking at our Grignards, we have to be very careful with them. They generate our carbon nucleophiles. They allow us to build larger structures, but they can act as bases. So we have to limit proton sources, which goes back to solvent and structural features. Okay? And they can self-react if there's another electrophilic site somewhere in the molecule. Okay? So that's actually a good point, just because I happened to notice and looked at this a little carefully. That last one, what are we looking at? What's the issue with that one? We have an electrophilic site, right? What's the issue with the next one? Well, that's kind of interesting, actually. They're highlighting the blue, which isn't obvious on this screen, but it's a little better on the other one. Why are they highlighting that position? Is that really electrophilic? So what's wrong with that site? Partial negative wouldn't be a problem. The carbon is positive? So the Grignard could attack that position? How many bonds would that carbon have?
Right next to each other.
It would have too many, so we'd have to break a bond. What bond could I break? Carbons or hydrogen? Can I break carbon or hydrogen? H minus? H minus is more stable than the C minus? No. Why are we circling that position as being reactive? It is not because it's electrophilic. It's because it's acidic because of the elimination possibility. Okay. Does it have an electrophilic site? Yeah. Right there. Why did they not highlight the electrophilic site? They highlighted instead the basic site or the acidic site. Grignard reagents are more active as bases than they are as nucleophiles. Okay, this is one of the reasons why we drastically control the environment in which they're in. Okay, we need to prevent that acid-base characteristics. The next one, what's our issue? They're hiding the blue, which means we have an electrophilic site. The next one. Well, this is a bit irritating. They aren't highlighting one atom, they're highlighting 2. What's that? Really what they should be highlighting is just the H because that is acidic. Okay? So we have to be careful with the Grignard reagent we choose and making sure it can't self-react. Okay? Make sense? Okay. So now the fun reaction. Okay. This one, in my opinion, absolutely deservedly so. Wittig gets to stamp his name to this because look at that reaction. We're starting with an alkyl halide, and we turn into an alkene by adding 4 carbons. That's just weird. We used, what is P? Phosphorus. Stop laughing at me. Okay. We use phosphorus. What the heck? We never use phosphorus. We've got 3 phenyl groups. That reagent right now is screaming what? What can you tell me about phenols? Steric hindrance. We've got a massively sterically hindered reagent to start. Butyl lithium stupidly reactive negatively charged carbon outright, and then I'm throwing in a polar pi bond into this. And somehow or another, all that magically together in this proper sequence gets us our final product. Okay? If there was ever a reaction to say magic, I think this is it. Okay? So what's happening within this? Okay? So what appeared to have happened? What things changed? Okay. Substitution. How do you see a substitution? Where are you seeing a substitution?
Bromine and phosphorus.
So somebody's looked a step ahead. Let's just look at what changed between our reactants and our products. Okay. We have a formation of a pi bond. Okay. We have a longer carbon chain. I don't see an oxygen. Lost the bromine. What's wrong with that? I know, I erased that. What else do we lose? Rhymes with oxygen, but it is not oxygen. We also lost a hydrogen. I mean, really, how many terms rhyme with oxygen? Okay. We only lost one hydrogen. Okay. So what reaction? We've got 5 reactions. Substitution and elimination and acid-base and what was that? Radical, and that's what this chapter's about. The last one. Nucleophilic addition. 5 reactions. Which of those 5 reactions does that? A mixture. None of those 5 reactions does all of that at once. So we've got a lot of crazy stuff going on in this, and we have to process our way slowly through it. Okay? So we've got 3 primary reagents, okay, which means 3 reaction steps. How many mechanistic steps if we have 3 reaction steps? Who knows? Draw the mechanism. Just because you have 1 reaction step doesn't mean you're confined to a certain number of mechanistic steps. The mechanistic steps could be thousands with 1 reagent. Okay? So we need to identify at each of our stages, what is our nucleophile, what is the electrophile, and then looking at our substrate and saying, what can it do? How does it work? When we hit step 2, the end of step 2 gets us a fancy new reagent known as the yllid. Okay? Germans? I don't know. But they called it yillids. Okay? Every step of the way through, evaluate each process. So let's look at step 1. What do we have? We have our alkyl halide, and we have our phosphorus. What do you see? Electrons. Where do you see electrons? Around the phosphorus and the bromine. So those would be potential. Keep going. Nucleophiles. Which one would we expect to be the better nucleophile, bromine or phosphorus? Why phosphorus and not bromine? Why is bromine a good leaving group? How many bonds can bromine have? 1. How many bonds does it currently have? 1. Can it share electrons to make another bond? No, which means it cannot act as a nucleophile. Why is that now screamingly awesome? What have we found? 1 nucleophile. Okay. What does that 1 nucleophile then need to react with? Our 1 electrophile. Okay. I heard someone say the bromine. Can the nucleophile react with the bromine? Why not? Keep going. Phosphorus is electron source. What does bromine have a ton of? Electrons. What happens when the negative gets near the negative? Nothing. Okay, so that doesn't work. It doesn't attack the bromine. What does it attack? the carbon attached to the bromine. Please don't lose track of this. We can kick out our bromine, and we end up with our final product. I lied. What characteristics would we expect in our final product? And since I just showed it there, maybe you...
Charge.
Why would you expect a charge?
Phosphorus is losing electrons.
Phosphorus likes to have.
Phosphorus was neutral, and what did it just do? Gave up electrons to make a bond. We would expect the phosphorus to become charged. What happened to the carbon? I don't quite accept nothing, but the right idea.
Exchange one bond for another.
It exchanged a bond for another. So it lost and it gained. The net result is it stays the same, and we'd end up with our final product. Okay? There we go. That's it. What type of reaction is this?
Substitution.
Substitution. What mechanism?
SN2.
Okay. We're likely doing SN2. Why would you say SN2?
Because if we had an SN1, you could get a rearrangement second to the.
This does become, what's that?
It wouldn't.
It doesn't do SN1. Why not?
It's a primary carbocation.
Okay. If we did it SN1, we'd be forming primary carbocation. We can't form that, which means SN2 dynamics. Okay. Does anybody have a problem with that? Said another way, I have a problem with that.
Super bulky, why?
Okay. Our nucleophile is massively bulky. Okay. Why would the phosphorus be able to do this?
Because the other one's not.
Phosphorus is big.
Okay. There's a couple arguments that would go into this. Number one, what is the shape of our phosphorus? Triphenyl phosphorus.
Tetrahedral.
The electron geometry is tetrahedral. Its molecular shape would be trigonal pyramidal. Let's just say that. Okay, which means that lone pair is now floating at the top of your structure. So the electrons are sort of available. But if we put a nitrogen in there, that wouldn't have worked very well. So what's different between nitrogen and phosphorus? Phosphorus is so much larger that what happens?
Kind of pushes those phenol.
There's more space. The phenols have a lot more space to occupy. That exposes that electron pair a little bit better, okay? Which gives us the opportunity for the phosphorus to act as a decent nucleophile. Okay? Make sense? Okay. So, because we're running under SN2, our best alkyl halide is a primary alkyl halide. We can run with secondary, but they're going to run a little bit slower. Should we use a tertiary? No. Now there's way too much steric hindrance. There's no way a tertiary is going to work. Okay. The next part of this is why are we doing this? Okay, well, this comes down to what that next step is. What I'm telling you here is giving you the answer. We're priming the carbon to hold a negative charge. We're attempting to make a nucleophile. Okay? So what happens in our next step? We take that triphenyl, or the alkyl triphenyl phosphorus compound, and we react it with butyl lithium. Okay? What is butyl lithium? Okay? We have all those carbons, and then we have what kind of bond between the last carbon and the lithium? An ionic bond, which means really what we should be doing is erasing the lithium and putting in a lone pair of electrons with a negative charge. A negatively charged species can act as what? We have nucleophile or base. Okay? The option between those two, that becomes challenging. What happens if it acts as a nucleophile? Where would it attack? I'm going to guess. I'm saying the nucleophile is the top one, but I don't know. Okay, the nucleophile will attack the phosphorus. What's our rule for Lewis structures? Octets. So if we attack the phosphorus, which is positively charged, what would happen? We have to break the octet. We have to kick a group out. What would we kick out? A carbon, a negative carbon. Did that do anything to stabilize our negative carbon? No. Did it do anything to stabilize the positive phosphorus? No. It takes it right back to a positive structure. So attacking the phosphorus, not a good idea if it's going to act as a nucleophile. Where could it attack?
The carbon.
Could attack the carbon, kick that guy out, And we would end up doing, so 1, 2, 3, so now we got 4, 5, 6, right? Everybody see that? What if it acted as a base? It needs to remove what if it's going to act as a base? Hydrogen. Where are their hydrogens? Red, blue, purple. Which hydrogen is the most acidic and why? The red has a good leaving group. That's an interesting question. If we removed that hydrogen, is there anything that would leave then at that point? No, it's directly attached to that position. That doesn't work. Blue had a decent leaving group because then we could kick out the phosphorus. So that I agree with as a potential leaving group. Should have shown that with blue. Okay, what else could we potentially see? Two people in here asked questions about this in office hours, so I know they know the answer.
Mum's the word.
Mom's the word. That's appreciated. Our base could attack the red hydrogen. Why would the red hydrogen work? Okay. What would we end up with? 1, 2,
Structure of resonance.
phosphorus. Why would I potentially do that? Why would that hydrogen be a good one to remove?
Didn't you want to make a carbon nucleophile?
Okay, so we've got a couple directions we can go with this. Number one, the whole point of this section was carbon nucleophiles, so it probably makes sense to make a carbon nucleophile. Okay? But why would I make that carbon nucleophile? There's a resonance structure that does what to the charges? Stabilizes them. I don't feel like writing it all out. Okay. Anybody have an issue with that resonance?
Phosphorus can't keep that.
Why not?
Breaks off.
It breaks the octet. Can phosphorus exceed the octet?
Yes.
Yes, unfortunately. Why?
Because it has a d orbital.
It has access to the d orbitals. Your third row, anything in that third row or lower, can exceed the octet given the proper circumstances. Guess what this is? Sorry, Jen. The proper circumstances. Okay, we can break the octet here. This is one of the reasons why nitrogen does not work in this case, because nitrogen would never be able to break the octet because it's only in the second row. Okay? So we do have this possibility for stabilizing that negative charge that we wouldn't get in any other circumstance. Okay? The power of this is that we have now generated, as Jen initially pointed out, we have generated what? A carbon nucleophile. What can we react to that carbon nucleophile with? An electrophile. And that would be in our next step. Hey, look at that. I even set it up right. Okay. So our resonance stabilization aids in the formation of our yelid. Guess what that structure is called? A yelid. Okay. We're looking at a doubly charged structure immediately back to back with that resonance. Okay. This gets us our big carbon nucleophile. So what do we do in step 3? So you might already be going like, sweet, I like seeing that word. What's the word up there that you might be like, yes? Try again. That could be a fun word. But I personally would look at this and see the word debate and think. What am I thinking as soon as I see the word debate? I don't need to know it. Okay? This is an argument that is actively up for debate on exactly how this reaction works. That simplifies what I have to learn and figure out. Okay? Does that mean you don't have to think about it? No, you still got to work through it. Okay? So let's look at it. What do we see? We want to. Where do you see electrons? Okay? Oxygen versus the carbon being our electron source. Which one do you think is more likely? Why the carbon? It's charged. There's our answer. It's charged. That's why the carbon's more active. Okay. What does that mean? We have a nucleophile. What do we need to find? Where do we have to find that electrophile?
Polar pi bond.
In the polar pi bond on our carbonyl carbon. What happens? Our nucleophile can come in and attack. We end up breaking our polar pi bond, and we would end up with, wait a second. What happened there? Didn't we have our nucleophile come in and attack the carbonyl? Okay, so that would be this one. And that attacked the carbonyl carbon. Okay, so I can see that bond. We broke the pi bond, so that's no longer there. So no pi bond. What the heck is this doing?
That's, if you break the pi bond, you get a negative charge on the oxygen.
We'd have a negatively charged oxygen. What is the charge on the phosphorus?
Positive.
Positively charged. What's going to happen if we bring a negative near a positive? They like each other. We end up forming another bond. And that is our purple bond. Okay. What issues might you have within the system? Okay, we've got lots of steric arguments setting up in this. Okay, but remember, phosphorus is large, which then means it can set up a proper balance to be able to alleviate that strain, and we aren't really forming a full-on, what is that, square? Okay. What else might be a problem with that? Jen, you had a complaint about this before.
We break octet.
We broke the octet on the phosphorus. Can phosphorus break the octet?
Yeah.
Yeah, so it's kind of okay. Okay. Does it want to have its octet broken? No, so what needs to happen? It's got to ditch the carbon. But then that carbon, okay, which carbon would it be ditching, the red one or the blue one? Red one, because it's attached to the phosphorus. That red one would then be carrying what charge? A negative, because we're trying to get rid of electrons from the phosphorus. Okay. Can carbon hold that negative charge? No, so what is it going to try and find? A positive. It's negative, remember? So it needs to find a positive. Where is there something positive nearby? Why is the blue carbon positive? Because the oxygen is electronegative, drawing electron density away. Okay, so we can take our electrons between the phosphorus and the carbon and share them between those two. But now what's our problem, Jen? We broke the octet on the blue carbon. So what needs to happen? Break off the oxygen. And what's the result? Okay, and this is where I would argue you should draw it ugly. And we would have phosphorus with our phenols and a negative oxygen and officially a positive phosphorus.
Is that still a unit?
Okay. Actually, I think technically, because I think you can it's classified as a carbonylid, is what we were looking at before, and so now it's no longer a carbonylid. Maybe an oxygen ylid.
Is that an ionic bond between oxygen and phosphorus then?
Technically, yes, between the negative and the positive, yes. Not the sigma bond between them. Okay. What happens between our oxygen and our phosphorus? They actually form a pretty solid, strong bond. It's a much stronger bond than between the phosphorus and the carbon. Okay? And that solidifies and stabilizes that structure. Okay? The end result, we get all those happy pieces. Okay? Anybody notice anything interesting about the double bond formed that we should say maybe be concerned about?
It's not the structure we have.
No, it's the structure we're supposed to have. Yeah. It's a trans double bond. Okay, every time we make a product, we have to evaluate the isomerism of it. So when we generate stereocenters, we have to look for R and S and think about that. When we generate double bonds, what do we have to think about? Cis and trans.
Is that the same one? You started the original products that you had on the couple slides back was the cis form.
Okay, never mind. I see what you're saying. Okay, so we have a cis-trans issue to address. Okay, this is one of the larger issues within the mechanism debate. Okay, the larger issue being, depending on the conditions, you can force the trans product primarily, or you can force the cis. Okay, those conditions vary wildly, which then means, what do you need to know?
Which one is?
Wittig produces two products. the cis and the trans product, assume it's a 50-50. Okay? And a lot of that comes down to what is happening in that system. Okay, why? What is special about the structure that I've got drawn in purple circle? Anything jump out that you're like, oh crap, I've got to worry about that now?
Stereo centers.
A lot of it centers on those two stereo centers and how they affect each other. Okay. It's those stereo centers and then the sterics generated by the phenyl groups and everything else. Okay. Those kind of dominate and dictate how we end up with cis or trans. Okay. So altogether, what we end up with is both, oh, see, look, I had planned that. We can convert our carbonyl to an alkene with a carbon chain lengthening, okay? Pretty awesome. I can get a larger carbon structure, and I maintain the chemistry of the structure because I have an alkene. The alkene I can then do what kind of reactions with? All kinds. I won't quite accept all kinds. I could do radical reaction. What type of radical reaction could I do? Radical substitution. We can put bromines in on the hydrogens. Okay, or we could do radical addition. Addition was what you were saying, not the elimination. And we could put our hydrogen and bromine on the structure in an anti-Markovnikov fashion. So we could do radicals. What else could we do? And radicals kind of an unfair one because you could always do radicals. You could do, what was the first part of that? Not the water or the oxygen. It was add. We can do an addition reaction. Okay. Acid-base substitution. None of those really fit. We're really running the addition reactions in these. Okay, additions or radicals. Okay, so it's looking at the structure and saying, well, what can I do with it? What more can I do? Kind of makes sense? Okay. With that, here we go. 3 questions. Work through a couple of them. See what you can come up with. I'll draw up the answers in just a second. Get started. Is look at our reactant and our product and find where we have similarities. Where did these 3 carbons go in the product? Okay, those are our top carbons. Where did these 4 carbons go? At our bottom. And the double bond of our oxygen has disappeared, and instead we no longer have the oxygen, we just put the carbon in that location. Okay? So understanding the mechanism is an important aspect, and I will ask you to kind of go through and do mechanistic steps. Beginning to end, this is not one I would ask because it's a debatable mechanism. Okay? So how can we use that pattern, now as we frantically punch through a bunch more slides, to help us out here? Okay, well, I would argue that I want to redress the issue of the carbonyl. Okay? That is known as your condensed formula, which is the biggest load of crap perpetuated on organic students since the beginning of time. Okay? That formula removes all information about what is happening within the structure and makes it very difficult to interpret. So don't work with it. Spend your time to first interpret what that structure looks like before you move on and deal with anything else. Okay, so I have a CH3 connected to a carbon with another CH3 and my carbonyl oxygen. So we drew that on the bottom. And on the top, what should I draw?
The line structure for the phenyl.
The alkyl halide. Okay. What happens in the Wittig reaction? Ta-da! Okay. You can work through the mechanism. That is fine. Okay. The larger issue, particularly with a question like this, what is the answer? You don't need a mechanism. You need the answer. To find that answer, you have to recognize the patterns that you're working with. Okay? So when you go through and look at the reagent list, find where things are and find the things that changed. If you think you're doing a Wittig reaction, it is usually really, really easy to just draw out your carbonyl and say, okay, I don't want the oxygen anymore, and I'm going to replace it with the carbon from my electrophile or from my alkyl halide. It was at the 2 position with 1, 2, 3, 4 carbons, and there we go. Notice one of the checks that I went through and did is counted the carbons. Okay. Why? The Wittig reagent, more than any other reaction, students have a habit of adding a carbon. What carbon do they end up adding? Kind of a weird statement to make. The carbon students end up adding the oxygen. The oxygen magically becomes a carbon. Okay, what do I mean? You end up drawing something like this.
Doesn't have to.
Okay? We've added a carbon. If you can count your carbons, you can acknowledge that that is an extra carbon, and you can try and track down where you added it. It's then just a question of fixing it. What about the next one? It's the same thing. So I would again draw out my ring. Okay, there's my carbonyl. Okay, the carbonyl needs to get, or I need to get rid of the oxygen and replace it with the carbons from my Wittig. Looking at my Wittig, I'm looking at what type of Wittig? Primary or secondary? Primary. Okay, the Wittig reagent is that carbon. There's only one other carbon connected to it. And I have three carbons. 1, 2, 3. So there's 1, 2, 3. You saying that because you like that? Or you mean like that was magic? Don't do that. Okay. It is. It is just too easy, but it works. Okay. That's what we're trying to identify. In a synthesis, how could we make this more difficult? The product that I end up trying to get you to find would be the alkane. And you'd be like, well, how did you get the alkane starting with something like this? We'd have to remove the double bond, which we don't know how to do yet, so that was a bad example. Okay? But we could hide the alkene. Okay? We could hide that chemistry behind other functional groups. Yes?
So we would always get a 50-50
Of cis and trans. Yep.
trans, so that on that second one, there would just be on the other side that change.
Yes. Okay. Providing 2 Wittig reactions to go the opposite direction. Okay. The Wittig one we're breaking is the one in purple. Okay. What would I expect to be different about steps 1 and steps 2? Rhymes with something. Yeah, nothing. Okay. We need to add the triphenylphosphine, and we need to add the butyllithium to this. Okay. Step 3 is where it would be different. Okay. And step 3 is where I'm bringing in the carbonyl. Okay. What carbonyl do I want to use? Okay. Well, I'm reversing this, so I can either erase this half and put in an oxygen, or erase the other half and put in an oxygen. Oh, look, there was 2 ways to do it. I wonder why I asked you for 2 ways to do it. Actually, I don't really wonder that. Okay, so let's say we erased that half. Okay, so I would need that carbonyl, but what would I react it with? What was the very first reagent I would use? That first reagent needs to supply those missing carbons, which would then be those. And I would be starting with, right? Okay. What's the other method I could have done, which I'll show in black? How many carbons? 3. 2 syntheses. Do both of these syntheses work equally well? Probably not. Dang it.
Second one works better.
Why does the second one work better? I like it.
Primary.
Think back to the very first step of our Wittig reaction. The complication was we're running an SN2 reaction with a highly sterically hindered phosphorus. Okay? We want the least sterically hindered alkyl halide we can. This is our best answer for that Wittig reaction. Okay? Which in theory we'll box in here in just a second as soon as the computer catches up. Catch up. Or just delete all my work, that's fine. This is our best product. I did see that hand. Yes?
So in the second one with the benzene there, how come we don't have the lithium in that reagents?
Why was the lithium, and actually for that matter, the triphenylphosphine? I don't see triphenylphosphine listed at all.
So lithium acts as a base to create the that's
Triphenylphosphine reacted with our alkyl halide. The butyllithium reacted to form our yllid. What is this species right here? That is the yllid. Okay. That structure, and this is exactly why I drew it, so I do appreciate you asking that question. How did I get that reagent? I did the first two steps already to an alkyl halide. Okay. Why would I do something like that and show it like this?
that's what ACS I did.
Okay. What is the pattern that most students try and go through and do? Wittig means alkyl halide plus triphenylphosphine plus butyllithium plus my carbonyl. I don't have an alkyl halide. Oh, this must be chemistry I can't do. Okay. They're hiding the chemistry by shortcutting the amount of work you have to do. Okay. But because you aren't used to looking at the chemistry behind it and instead focusing on the reagents too much, you lose track of that. So that's why that happened. Does that make sense? It's an easy thing to lose track of. This is where you should go back. Where's the chemistry? Double bond. Which one's more electronegative, carbon or phosphorus? Carbon is actually. Then means it's negative, it's positive. Oh, I have a negative carbon. Oh, I have an electrophile. Let's hook them up. Oh, shoot, that looks like the Wittig. Okay, make sense? Questions about any of that? Yeah, you guys seem to really like the Wittig reaction. Okay. Remember the part where I at least got people smiling on? Just erase, draw. Erase, draw. It's lovely. Okay.
Could you accept an erase draw on a test?
So how could it get asked on the test where I would not accept an erase draw?
Show all the mechanisms.
Show your mechanistic steps, but the mechanism was debatable. Can I ask that question? No? So try again. How else could I ask it? Multiple choice. In the multiple choice, what can you do? Erase and draw. There you go. Okay. So,
since the mechanism step is debatable, what's the other debatable portion of it?
it's coming down to how that phosphorus oxide carbon structure links up and how it decomposes and how it falls apart. Because we don't have a clean mechanism, we can't predict cis and trans quite as easily. Under certain circumstances, we can prove it, but then someone changes the conditions and says, well, I get a different product with close to the same thing. Why? So there's a lot of things going on in that step that we don't have a solid understanding of, primarily probably because of what we're about to look at right here. Phosphorus. Phosphorus and its d orbitals. It's those d orbitals that are messing with how the electrons shift through the structure, which then makes it a little bit more difficult to predict how things are aligning. We just aren't there yet. Okay? So when we're looking at our phosphorus, we do have that resonance. Which of those two structures is the best structure to show?
The non-charged.
Okay? One on the right, non-charged.
Charged.
Oh, you're shaking your head. And you guys can't
You know
answer
the
it, but
answer.
Sean, shaking your head. Why? Why should the charged one?
Exceeding the octet.
But it doesn't matter. It
Lower
multiplies.
energy.
Heh, I didn't even look at that one. Yeah, not exceeding the octet. Is that going to be important? Yeah. If we look at our Lewis structures, our order is actually, our Lewis structure number 1 is don't go under the octet. Okay, why would we go over the octet? And Lewis structure rules, the reason we go over is to minimize charge. Is that what we're doing? Yeah. So why is the one that's charged better than the one that's uncharged? It's all going to come down to looking at everybody's favorite Newman structures. Okay. we'll draw the Newman structure for the carbon in front. Okay. The electrons for that carbon, since we're trying to oscillate back and forth between a negative charge and the pi bond, let's just go ahead and show it as a p orbital, okay, forming the pi bond. Now let's draw the phosphorus in back. Typically when we would draw it, we just draw it like this, right? There's our back atom. Everybody okay with that? And then we could draw, you know, the other p orbital down in behind it. Okay. Why are we drawing it like that? What is typically our back atom? Carbon. What's the difference in size between carbon and carbon? There isn't one. What's the difference in size between phosphorus and carbon?
Big difference.
Is there much orbital overlap? No. If there's no orbital overlap, do I have a pi bond? No. Okay? So it does not make sense to show it as the carbon-phosphorus double bond because there's not enough overlap to cause a double bond to actually be forming. Okay? It's kind of a nuance of it, so don't panic on it. There's a bunch of other stuff that I didn't really care about, so we'll just skip that. Okay. Retrosynthesis, we just looked at the possibility. What can we do? Whoa, that was weird. Sorry. Just ignore the man talking to himself. We could split it. Just bring in our carbonyl and the halide, or we could have done it the other way. Our halide and our carbonyl. Make sense? So this is the kind of erase and draw, except we're unerasing and drawing.
Is there a reason bromine?
Does it matter which leaving group we use?
Well, it's a good leading group.
It needs to be a good leaving group. Okay. So bromine will typically show there. What if we used water? Isn't water a good leaving group?
That would exceed.
What if I just put in OH?
You have to be in an acidic environment.
We'd have to change the environment. We'd have to move into acidic conditions to allow that to happen. Acidic conditions can potentially mess with our reagents. Take it a step further. We have to do that because oxygen with our alcohol has a bunch of chemistry available to it. We want to limit that chemistry as much as we possibly can. So we want to pick a halide. Could we have picked iodine? Sure. Chloride? Probably. Why bromine? It's a great little leaving group. Doesn't do a whole lot else once it leaves. Okay, so you'll typically see it with the bromide, but pretty much any of the halides except for fluorine, okay, would work. So, that's a tight space. The sulfonium ylids, your textbook talks about this. Okay, I only include it in here for one particular reason. We end up generating, okay, our sulfonium ylids, so we're asking about what is a ylid. Okay, here we have a ylid with that negatively charged carbon. This is awesome at doing what? Generating a methyl anion, okay, or a methyl nucleophile. This is super, super useful in biochemistry because a lot of the methylating agents or a lot of the reactions done in biochem with methyl groups, they're going through a sulfonium ylid. Okay, they're using sulfur to transfer a methyl group around. That's about all I really have to say about it. Okay, but it's doing ultimately the same thing. So more kind of yada 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 stuff. Okay, we good with the two different methods? I'm going to take that as a yes. Here's our spider diagram. What we've covered now within this chapter is everything on the top half. We've got all of that fun stuff now covered so far within the last, week or 2 weeks. Okay. So what we now need to move to is this last little section. Okay. And this last little section is talking about modifying the carbonyl to make what is known as an alpha-beta unsaturated ketone carbonyl. Okay. Why is it alpha-beta? The carbonyl is our 0 position. The first position after would be alpha, the next position, beta. Between the alpha and the beta position, do they have all their hydrogens? No, so it is unsaturated. I have an alpha-beta unsaturated carbonyl. The alpha and beta are just a way of nomenclature referencing the location of your double bond. How does that change our chemistry? Okay. What chemistry do we get from the carbonyl? Not that the box is supposed to provide any extra information or anything. We have an electrophile. Why was it electrophilic? The pi bond can polarize, removing electrons towards the oxygen, because oxygen is more electronegative. Do I have anything that could potentially stabilize that positive charge? Not that that really thick purple line that's hopefully showing up is to give you any hints. Okay. We've got another pi bond that can do resonance over, which then does what to that last carbon? Makes it positive, and guess what do we have? And another electrophile. So the instant we move to an alpha-beta unsaturated carbonyl, we have two sites of electrophilic characteristics, okay? Which means we now have to evaluate which of those sites is more likely to react. This is really getting at our kinetic versus thermodynamic. So if you haven't watched that video yet, it's probably a good time to do so, because you're going to get some review on this, okay? Our strongest nucleophiles. So nearly everything in chapter 17 will attack our carbonyl electrophile. Why would we attack the carbonyl electrophile? Which one is more positive? Which one's more electrophilic? Carbonyl, carbon, because polar pi bond. Okay. Why would the strong one react with, or strongest, react with our most positive?
The strongest is the least stable.
Strongest is the least stable. It's going to react as quickly as possible to neutralize that charge as quickly as possible. So it is going to zero in on the most positive thing possible. Virtually all of our nucleophiles so far discussed in chapter 17 are what I would call stupidly strong, okay, or our strongest. Everything up in that category, stupidly strong. Where do they attack? Carbonyl carbon. What happens if we shift to now just a strong nucleophile, okay, like oxygen? Okay, well, that is now not as strong of a nucleophile. It can just kind of chill around and say, well, I'm going to react where it makes the best product. One case where we're reacting as fast as we possibly can. One case where we're forming the best product. We have kinetic and thermodynamic. Okay. Deciding which one we get comes down largely to identifying the reactivity of our nucleophile. Okay. And while I would love to continue into this, we unfortunately have to stop because we are at time. We're moving not anywhere near the pace I want to move, but we'll deal with it as we come to it. Okay. Thursday, we'll look at Wednesday, we'll look at the difference in reactivity on our alpha-beta unsaturated carbonyls, just getting at thermodynamic versus kinetic. Okay. Hopefully Thursday, we will also move into the acetals. Okay. The lecture portion of acetals is very, very, very tiny because most of it is in the online video. Okay. So it'll be more just kind of practice with acetals, and hopefully Wednesday as well, we'll move into nitrogens as nucleophiles instead of just oxygens. Okay. If we do that, then we might be on pace to get through all the material we need to for the exam. Otherwise, we're going to keep pushing material into the next exam. Okay?